due to, I should say, due to moderate wall brushes, because if you ram into a wall, the rotor is going to go anyway. So, as I said before, well, with this vehicle, we have the ability to have internal rate damping. And our strategy now is to have internal rate damping and follow walls to navigate inside a indoor environment. And this strategy is reasonable because it allows us to traverse most of the indoor environment in a reasonable amount of time. If we can actually get the wall following thing to work and have the information about how far the wall is. So the traditional control strategy, this is what we've been doing in outdoor UAVs, is basically to control position, you must first control velocity. To control velocity, you need to control attitude. This is for rotorcrafts. We're talking about rotorcrafts here. And to control attitudes, you need to control the rates. And rates are actually controlled from actuators. But what we're going to do here, and what we're proposing, is to directly link position to actuators and have the vehicle internal dynamics take care of the middle loop, basically the velocity and the attitude control and the rate control. So we're basically relying on inherent damping and connecting position directly to actuators. The control architecture is pretty simple. This is a diagram for the attitude control. The other loops are similar. So what we do is we separate, this is very common in rotorcraft control, we separate the control loops into 4 different loops, which is altitude control, lateral control, longitudinal control, and rudder control. And then we couple them together. So the altitude control basically is a command that is given to the controller by an external source. It's basically a PID implementation, which means there's a proportional part, there's a derivative part, and there's an integral part. Now, due to the dynamics of the rotorcraft, it's really important to have a derivative part. Basically, that allows you to have damping in the vehicle. But to have derivative part, you need to know the velocity, which you don't know. All we have now is position sensors, which are, for example, local range sensors like sonars or IR sensors. So, it's not a good idea to actually numerically differentiate these range measurements to get the velocity, because you're going to end up with really high noise and weird numbers if you somehow get an outlier, because you don't really know when you're facing an obstacle, you don't really know whether the obstacle is moving or whether it's stationary. You don't know the topography of the obstacle. You don't know anything. So you have to be really careful with what you do with those measurements. So we proposed using a Kalman filter based estimation of relative velocity. That's what we call it, the relative velocity to an obstacle. And that is what we came up with is a there's three main things that separate this PID implementation from a standard PID implementation. The first one is a high confidence and low noise Kalman filter estimation of differential terms using what we call as an outlier detector. The second thing is inbuilt saturation protection. This is what we propose in the paper, is to use the control outputs for the integral term instead of using the errors. And third is what we call phase scheduling, and I'll talk about that soon. So, alright, so suppose we have this Kalman filter that gives us relative velocity to obstacles. And we have the vehicle that is following walls, which is actually of the coaxial type. When you're close to walls, the rotor inflow from the vehicle actually interferes. The wall interferes with the rotor flow, and that creates some kind of non-linearities. Our pilots describe that as basically if you're a little bit away from the wall is trying to push you. And if you cross a certain boundary, then the wall tries to pull you towards it. So there is some kind of non-linearity there, and the whole assumption in PID control is that everything is linear. So we need to account for this nonlinearity with something. And normally this is done, a very standard way of doing this is using gain scheduling or adaptive control. But adaptive control is a little bit hard in this case because this would be what is called as an output adaptive, like an output, because you don't have full state measurement. So it's an output based adaptive control. You have to pretty much guess what your states are. And that's not the best thing to do. So what we propose is to do gain scheduling. But traditional gain scheduling is done based on the states of the system. For example, in a rotorcraft, you would have different gains for the hover mode and different gains for the forward flight mode. But here what we want to do is we actually want to have different gains based on where we are in the room. And so we came up with this concept which is called phase scheduling. So So phase scheduling is basically looking at the phase plot of the error system, of error dynamics of the controller. The error dynamics are basically the rate of change of error, which is error dot, and the actual error. If you just think about it, if you're controlling a particular distance from a wall, and if you cross that distance and are actually closer to the wall, then your error is negative. And the error here is the difference between the commanded position and your actual distance from the wall. If you're approaching the wall, your error dot is also negative. So we proposed a method which basically, in only one quadrant of the phase space, which is plotted there, it can be considered as error dot versus error. In the quadrant where error and error dot are both negative, we use high gains. So that this is a quadrant where you're most likely to hit the wall, and you're probably very close to the wall. And in all other quadrants, we use low gains. And we came up with a linear interpolation for transitioning the gains between, so to have a smooth transition of gains between the high and the low gain parts. And this is what we call as phase scheduling. And phase scheduling has been really useful for us because the rotor, like I said, has a tendency to get sucked into the wall as it gets closer to the wall. So it's really hard to come up with one set of gains that'll keep it away from the wall and also keep it within a certain distance from the wall. So for navigation, as I mentioned before, we use commercial off-the-shelf range sensors, which are really low cost, basically sonar sensors and infrared sensors. We use two infrared sensors mounted on the front that give us distance to the wall, and the difference between the two sensors gives us heading to the wall. We have two infrared sensors mounted, one to this side and one to that side, that we basically use for obstacle avoidance and detection on the sides. And we have a sonar sensor that is mounted directly downwards that we use for altitude control. We use Kalman filters using a simple observer-based model to estimate the velocity or the derivative of these relative ranges. This Kalman filter has an elaborate outlier detection logic that we have developed in-house, which basically takes care of the peculiar noise properties that these sensors have. For example, a sonar, if it does not get a return, it'll just return max range. Now that is not very Gaussian, so this is not the assumption that you make when you design a Kalman filter. So what we have done is we actually are monitoring how the range measurements are evolving and trying to actively detect outliers and reject them from ever reaching the Kalman filter. And this way, the assumptions of Gaussian noise on the Kalman filter are a little bit more entertaining. And another key aspect of this implementation is that we can actually propagate measurements using our estimate of the velocity in case we have bad measurements for a limited amount of time. So the last thing I want to talk about today is a rapid method for validation that we've also used at Georgia Tech for this particular project. And this method is based on MATLAB. And I'm not talking about prototyping in Simulink and then converting that code to C. I'm talking about actually having MATLAB code run off-board as the main control logic and communicating with the vehicle using that code. Now many of you will say, oh, MATLAB is so slow and all that. That is all true, but MATLAB in the end is very user-friendly. You have access to a lot of functions that are just there for you to use. For example, you don't have to have any matrix multiplication functions. You can use LQR, Kalman filter functions to come up with the gains. And it makes it very easy for a person who is not committed yet to go deep down into the hardware and start coding because we're not sure whether this is actually going to work or not. So we came up with a very simple method of validating our guidance, control, and navigation software. This method was to basically use an off-the-shelf Arduino processor, which is it's not really powerful, but is able to read sensors and transmit that information out using an XB. We connect an XB with a USB to a laptop, which reads in this information. We use interrupts in MATLAB. MATLAB has this function. MATLAB 7.1 and higher has these functions, which can actually read serial ports using interrupts. We read in that information into MATLAB. We calculate the control logic inside MATLAB and send that information out using a trainer port on a RC controller. So RC controllers can usually have trainer port that can be connected to another RC controllers where the pilot can have selective control. The training pilot, basically the pilot who's trying to learn how to fly, can only have control of, for example, the altitude loop or only of the pitch cyclic. We can